So when we open the trace, this is how it looks like, and we have selected the heap allocations and outstanding size by process and handle option. You see that continuous leak.exe is on this window. This means that when we started tracing, continuous leak.exe process was enabled for tracing. Uh, Generally, as soon as we see the process we want to investigate, we do a filter on that process. So we say that filter to selection. I'll explain you these windows and the various options. Before that, let's look at the most important part, which is you need to have the symbols loaded. We saw that in the other videos that how to load the symbol and how much time it takes to load the symbol, how to configure the symbols. Once you configure the symbols and you've loaded the symbols, I would say then you're ready for investigation. But what I've seen is that even though symbols are not fully loaded, you could still see a lot of things and the stack that you want to investigate. I'll come to stack in a bit. Let me explain you the various windows. So this window here is the one for the processes that we want to investigate, and of course it is enabled, and when you click this you see that the color changes. So this is the color with respect to the graph which it is showing in this window. uh, you are seeing the graph going up in a very linear fashion, and then at this point it just goes straight, it doesn't go up. What does this really mean? Okay, let's look at the x-axis. X-axis very nicely shows the bytes of memory which has leaked, or in other words, which is outstanding. It calls it outstanding. It doesn't really call it out as leaked because uh, you never know this is leaked or not. What is the definition of leak? Leak is you allocate it and you never deallocate it. That's what leak is. Now, the trace doesn't know that did you allocate it at any other time, or is it just that uh, it shows as allocated now. In other words, is it that you allocated the memory now and freed it at some other time which is not captured in the trace, or is it that you never freed? So these are the two differences, and it calls whatever allocations it is seeing as outstanding, right? So down below on the y-axis you have the time in seconds, and of course nanoseconds. So I would say time is in nanoseconds. And on the x-axis you have uh, um, the amount of heap which was allocated. So looking at this graph, I would say that I see allocations, but I really don't see any deallocation. The memory here, which is about 1.4 MB as it shows in the graph, has never been deallocated, at least till the trace was taken. And how long was the trace taken? You can see the seconds here. So you see from 0 to about 26 seconds. That's what this, the lower graph also shows you. And I'll come to the lower graph. It's very interesting. We have line 1, then we have the process name. Of course, this is what we want to investigate. Continuous leak, as the name suggests, it leaks memory in our simulation for memory leak. Handle. Now what is handle? A good thing is that you can always hover around your mouse on the column that you want to know more about. So it's handle. So it says the heap handle containing the allocation. So as we know that the heap uh, has handles in native memory. So every heap has a handle, so you can always track a heap allocated under a handle. So that's why the handle column is there, and you see that that's the only handle we have. It's a small, it's a simple application which I made, for which just wants to you know allocate on the heap and never deallocate. So that's why you are seeing this graph which goes straight up, and uh, it is steady here. That just means that the allocation has stopped. So you can say that after the 18th second in the trace, no, not 18th, actually this would be, yeah, 18.7. After the 18.7 second, the till 26 seconds, the allocation is actually stopped. So you're looking at around about 8 seconds where allocations have not happened. Um, it could be the time the trace is just the application, which is the Windows Performance Analyzer, is just busy collecting the trace, so it doesn't show you any allocations further, because what this program does is it just allocates in a loop. So you would only expect this graph to go up. uh, so coming to other columns here, so we talked about handle. Now when we expand handle, then we have something in the stack column. Now looking at stack, it's basically all the functions that are responsible for allocation, right? And because of these symbols, you're able to resolve these function names, right? But if you don't have symbols, you would not see the function names here. So symbols are extremely important. Now we see that the stack shows, and this is where the stack starts. So n/a, I'm not extremely sure what it would mean, but at the moment, and also generally we start with the root stack. So this is where the whole story starts, right? And what do we see here? There is a call for user thread start, and as soon as we click a function, a part of the graphical view gets highlighted. So you're seeing that when I'm clicking this blue section is highlighted. So what it means is that this function somewhere is related to the various lines you are seeing, right? So this comes under what you call the time period of the graph section that you are seeing. So as in when I expand this stack, I see that now this looks like one thread. So this is the worker thread, and this is actually my program, right? I wrote it so I know, but you could also make out that this is a thread which is very specific to the code for continuous leak. Why? Because there is a module name here, that is continuous leak.exe bang, and then there's a function name here. So this function, as the name, I mean, you would have to do some guesswork if it is not documented well enough on MSDN, but I would guess this because of the name SEH. This is somewhat, and also the name CRT. This is somewhat related to the the C or the runtime, and SEH would be structured exception handling, right? So with my experience, I can say that this is, I mean, they labeled it, but actually this is the start of the whole story in terms of the other function which will be called under this function, right? Or after this function, or within this function. So within this function, we have a call of the main call. So the NEC C++ application has the main call, and after main, there is a new call which has been made. So we definitely now know this is for the heap, and that's what we're looking at. So the new operator or the new call actually uh, makes a call into the UCRT base.dll. So this looks like one of those modules which handles the new operator, and that further calls the NTDLL. Now this is where actually your OS subsystem resides with respect to the memory manager. User mode memory manager calls, all of them, they all start with RTL, and what you see is that he's done a call to allocate heap internal. So actually this is Microsoft's internal code, and I don't know if it's well documented enough. So it's internal code for Microsoft to allocate the heap, right? Uh, then what do we see here? What's about this yellow line and the blue line? Everything on the left is what I would say is about the stack and the process. And when you click on one of those lines, inside the yellow and the blue region is where all the count and the aggregation is, right? And after the blue region, after the blue line is what is the what gets shown on the graph, right? So of course it has the legend, so that's the color for the graph, but the size in MB is what is displayed here. So if I remove this, what do we get? So the graph grows, right? So now to get the graph back, oops, now how do we get the graph again? So let's see. Okay, let's go to the columns. More columns, and that was size. See size somewhere? We have, oh yeah, here we have. Okay, so it went back to the same position where it was, so thankfully I didn't have to move it around. But you could definitely move the column around, like if I move it inside, you know again the graph goes. So if I put it back here, the graph comes. So I could actually also bring the count here, which will have the similar graph, because the count is also a representation of how the memory leak or allocation would happen. So let's just keep what they have it by default, which is the size in MB. So what do we see here? Oh, if you talk about aggregation or summation, and of course you can hover and see what does this do. So this is change in heap usage in the current viewport. So viewport is this area, right? So what is the change in heap usage? Um, that's what it shows here. So what do we see is that this call, the RTL allocate heap internal, has is responsible for that 1.4 MB. If you convert the bytes into megabytes, that's what you see is 1.4 MB of leak, right? This is extremely important. This is extremely important information, that you can make out that the amount of leak is 1.4 MB, and we see count. So this is 369,646 counts of heap allocation, right? So it took so many counts for this amount of memory to be allocated onto the stack. And all throughout our program, till 26 seconds, we don't see the graph coming down. Had the graph come down, it would mean that the allocation happened and deallocation also happened. But we clearly see that allocation has not happened. Right? Impacting size is important in the sense, now look at and note that it's called impacting size. What that means is that it does have an impact with respect to how the graph is growing, right? So what it means is that this is 4 bytes of memory, and if you want to guess some more, this is of course an integer uh, type of allocation onto the heap, so it takes 4 bytes. So you see at 8.66 seconds, and this whole thing is a nanosecond number. So at 8.66 seconds, and you can see all the nanosecond details, you have a 4-byte allocation, and that's the one allocation, right? And after that, again, you see the nanosecond difference. You have another 4 bytes. So you're seeing how my for loop kept allocating memory onto the heap, right? So this is a typical example, or it's a simulation of heap leak, right? This is an extremely good example of how you would see heap leak onto your production environment, right? And and another very interesting thing that we see in the trace is that I could actually zoom in and see which part of this particular heap was allocated, or which part of, okay, where in time, if our time span is 0 to 26 seconds, where in time exactly was, were these highlighted heap allocations done. So if I do a zoom, okay, the zoom is not here, but it's on the, okay, you zoom from the graph, right? So now I've selected a small area, and you see that as soon as I've selected, that part below got highlighted, and this is this area onto the time graph. So it's definitely less than 2 seconds, and because it's saying 18 to 20, and it's actually less than a second. So I would say this is 19. Oh no, this is probably, yeah, I would say you call 1 second till here, 0.5 second till here. So yeah, it's less than 0.5 second. That's what I say. And I'm selecting this 0.5 second. Imagine I'm selecting this 0.5 second, and I'm going to do a zoom on this, right? So look at the granularity. Look how deep you can go. So this 0.5 second is right here. So all these allocations is what is highlighted. Oh, okay. So I stand corrected. Now look at this impacting size change. So whatever I've selected, now these allocations are not the one responsible, for this selection. So I'll actually have to go down till I see some impacting size. So here we go. So you're now started seeing this 4-byte allocation. So what I see now, yeah, what I'm seeing, what I used to see, and I'm sure we can see more about, is that when I click one line, that particular point in graph actually gets highlighted or changed. So you are seeing that, when I'm clicking one a line here, so this is 4 bytes of heap, and it's trying to change its highlighting. It's trying to highlight the graph the similar manner, right? So it's selected the whole thing, but I'm pretty sure if I zoom in more, I'll be able to come down to that granularity where if I select only that particular section will get highlighted. So yeah, here we go. So you saw that, and I guess I'm really deep. I'm at least in millisecond deep now. My zoom is, my granularity is now at milliseconds. So when you click here, you're seeing that this allocation is not in this time range, but is in this time range, right? So more and more I zoom, I can actually pick the exact time where this allocation was made. Let me tell you another very interesting field. You go to more column and look at the various columns it has. Uh, and the one I want to show you is this alloc time. Is there a dealloc time or free time? Yeah, free time. Free time is what we're looking at. So if you allocated this heap on the 18th second, and that of course there's a nanosecond deep stamp here, on the 18th second, if it was allocated, when was it freed? It was freed on the 26th second, but actually, no, it was not freed. I mean, it says it was freed, but you know what happened? I stopped the process. That's what happened. Or I stopped tracing, right? But which one is the 26th second you want to see? Well, that's just the end of the trace. You could unzoom everything, you know, and let's see our original, uh, you know, our original graph. This is our original graph. When does 26 second come? It comes here, right? And look at this second time stamp, if you may, is the 26 second. That is end of the trace, right? So what it clearly shows you is that allocation happened on the 18.17 blah 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 second, and the deallocation happened on 26.07 second. But actually, it's not deallocation. It's just that the process was killed, or the process was terminated. And when you terminate the process, all of the heap gets deallocated, right? So that's what happened. Or you never know. The trace was just stopped, right? Most likely the trace is just stopped. So there's no guarantee that this deallocation happened. It's just that you stop the trace on the 26th second. That's your end of a trace. Well, that's all I can say with respect to free time. So the time at which the memory was released, yeah, maybe not, right? Maybe may not be released, right? Because you could say that the memory was never released even after the 90th second, and the memory was never released. Or you could say, yeah, on the 30th second, actually the memory was released. So at that point, you have to take a call whether is this worth investigating. Is this the culprit for your leak? Was that something that was expected, or it was not expected? Is it impacting your process? All those things is what is your judgment, and this is that data.